Usually when we talk about looking something up, there's this expectation of manual labor.
Oh, yeah, definitely.
Like if you think about the old card catalogs at a library, it was a very physical, sequential process. You open the little wooden drawer, you physically flip through the index cards, you write down the Dewey Decimal Number.
It's an index,
Yeah.
like a very specific immutable coordinate in a rigid system. And if you misspell a word or if you just don't know the exact phrasing the librarian used, the system just breaks down entirely. You find absolutely
Yeah,
nothing.
exactly. You have to know the rules of the index. You find the coordinate, then you walk to the shelf, you pull the book, you flip to the index at the back of the book, you find the page. It's a whole pipeline.
It is. It's exhaustive.
But when you step into the world of modern artificial intelligence, that entire manual process, that rigid indexing is just gone.
We're looking at an information landscape today that, frankly, feels like magic.
It really does. It's as if the library itself reads your mind. Speed reads every single book in the building simultaneously and just whispers the exact answer right in your ear.
Which is, the absolute definition of a paradigm shift in information retrieval. We are moving away from systems that merely find documents based on matching keywords, and we're moving towards systems that actually comprehend the text within those documents.
And that is exactly what we are getting into today for this deep dive. We are looking at the exact architecture making that magic happen, which is open domain question answering.
Right, or just QA, for sure.
QA, right. Because what you're describing is the massive transition we're living through right now. We are moving from those old school search engines where you just type a word and cross your fingers that a blue link has your answer to AI that actually reads the internet to answer your questions directly. So for the person listening, okay, let's unpack this.
Yeah, let's do it.
Where do we even start?
Well, to really set the stage for you here, we have to define what open domain actually means in this specific engineering context.
Okay.
Historically, if you built a question answering system, it was constrained to a single, highly structured topic.
Like a chatbot on a banking website or something.
Exactly. Or you might build a medical bot that only knows about cardiovascular disease, or a transit bot that literally only parses train schedules. That is a narrow, closed domain.
Right. It only knows its one little world.
Right. But open domain means we are tasking a computer system to automatically answer human questions posed in messy, natural language about literally anything.
Anything at all. And the knowledge to answer those questions can't just be pulled from one neat little spreadsheet, right? It's coming from everywhere.
Oh, absolutely everywhere.
It could be pre-crafted knowledge bases like Wikipedia or DVpedia. It could be semi-structured data like HTML tables on a random website. Or, and this seems like the hardest part to me, it could come from completely unstructured web pages just floating around the internet.
Unstructured text is absolutely the hardest part.
Yeah.
By far. But, before we get into the plumbing of how an AI actually reads an unstructured web page to find an answer, we have to look at the types of questions you might actually ask it.
Okay, that makes sense.
Because from a computational perspective, human curiosity comes in a few distinct flavors, and they require completely different engineering approaches.
Right, because asking a machine, what is the capital of France, is a totally different cognitive task than asking, is the new sci-fi movie in theaters right now actually worth watching?
Precisely. The intent is entirely different. So the first flavor, and this is really the bedrock of open domain systems, is called factoid QA.
Factoid QA. Got it.
As the name implies, it centers on immutable facts. These are your classic WH questions, right? Who, what, where, when.
So, like, when was the Eiffel Tower built?
Exactly. Or who won the World Series in 2016? This is where traditional search engines have always shined, because the answer is usually a very specific noun or a specific date.
Okay, so factoid QA is pretty straightforward. Give me the facts, like a librarian handing you an encyclopedia. But what about that movie question I mentioned? Or like product reviews?
So that falls into the second flavor, which is opinion QA. And this is a fundamental different computational problem because it centers on sentiment.
Sentiment, right.
Think about an AI trying to answer questions based on product reviews on an e-commerce site or Yelp ratings. If you ask, does this specific brand of laptop have good battery life? The AI isn't looking for a historical date anymore.
No, it's reading people's opinions.
Right. It has to parse highly subjective human text, weigh it, and synthesize an answer based on aggregate sentiment.
And if you're listening to this right now, you're probably thinking the same thing I am, which is that people are incredibly weird and subjective in reviews.
Oh, incredible.
Like someone might give a laptop 1 star and write a furious review just because the delivery driver stepped on their flowers, even if the laptop battery is amazing. So opinion QA isn't just about reading, it's about filtering out human irrationality. It's like a food critic trying to summarize a vibe from a bunch of crazy people.
You've hit the nail on the head. Sentiment is noisy. It's so messy. And speaking of noise, that brings us to the third flavor, which is community QA.
Okay, what is community QA?
This involves pulling answers from crowdsourced platforms, think Reddit, Quora, or specialized coding forums like Stack Overflow. The system is trying to extract a factual answer from a thread of human-to-human conversation.
Wait, community QA sounds like a total nightmare for a machine.
It really is.
Because human conversations on forums are just full of slang, tangents, inside jokes, and terrible grammar. We use sarcasm all the time.
Constantly, yeah.
How does an AI even begin to parse that level of chaos? Like, if I ask a question on a forum, the first reply might be a meme, the second reply might be an insult, and the third reply might actually have the answer, but it's referencing the joke from the first reply.
It's a tangled web.
Yeah.
And you're touching on one of the most complex frontiers in natural language processing right now. What's fascinating here is that to handle community QA, the system requires a massive contextual window.
Meaning it has to read the whole page.
Yeah, it can't just look at one sentence in isolation.
Yeah.
It has to map the entire dialogue tree. It has to understand pronoun resolution, knowing that when user C says he is wrong, it actually works like this. The word he refers to user B, who posted 3 comments ago.
Oh, wow. Yeah.
Extracting clean, factual information from the unstructured, messy reality of a human forum is the ultimate test of an AI's reading comprehension.
It's like teaching a machine to not just read the words, but to read the room.
That's a really helpful way to visualize it, yes.
Yeah.
But here's the catch. To teach a machine to read the room, or to extract a fact, or to gauge an opinion, you can't just unleash an untrained neural network on the internet and expect it to figure it out.
Right. It would just absorb the chaos.
Exactly. You have to train it.
Yeah.
And training an AI requires giving it highly structured exams, millions of them.
Millions of exams. Okay, so we know the flavors of questions people ask. How do researchers actually build these tests to teach the models how to find the answers?
Well, one of the foundational testing formats is called a span solution.
Span solution.
Right. In a span solution task, the AI doesn't have to write an original answer from scratch. Instead, it is fed a passage of text and a question, and its only job is to identify the exact span, which is the starting coordinate and the ending coordinate within that text that contains the answer.
Okay, so it's basically like giving a student a neon highlighter and a history textbook and saying, highlight the exact sequence of words that tells me who the 16th president was.
That's exactly it.
The AI is just returning 2 numbers. Start highlighting at word 50, stop highlighting at word 52.
Yes. And the most famous data set used to train this specific highlighting skill is called SQUAD. It stands for the Stanford Question Answering Dataset.
Squad. I've heard of that one.
It's a massive collection of passage question answer triples. The passages were pulled directly from Wikipedia, and Stanford researchers actually paid crowd workers to read those passages and generate questions that could be answered by highlighting a span of text in that exact passage.
Okay, I want to pause on Squad for a second, because the evolution of this data set is actually a perfect illustration of how hard it is to train AI, right? Like the first version of Squad, version 1, had a critical flaw, didn't it?
It did. It had a massive blind spot. SQUAD version 1 only contained answerable questions.
Oh.
So every single time the AI was given a paragraph and a question during training, it knew with 100% certainty that the answer was hiding somewhere in that specific text.
It was guaranteed.
Right. The model learned that its job was to always find a highlight no matter what.
But that's just not how the real world works at all.
Not even close.
If I give the AI a Wikipedia paragraph about, like, the biology of dogs, and I ask it, what is the capital of France?
Okay.
An AI trained only on Squad V1 is going to panic.
It will.
Because it's been mathematically incentivized to always provide an answer. So it will just highlight a random dog fact and confidently tell me that the capital of France is a golden retriever.
Precisely. We call it a hallucination forced by the training objective. It would confidently give you a completely wrong answer just to fulfill its programming constraint to always highlight something.
That's hilarious, but also terrible for a product.
Exactly. So to fix this, researchers released SQUAD version 2, which introduced unanswerable questions.
Okay, so they changed the rules.
They did. They deliberately poisoned the data set, essentially, with questions where the answer simply was not present in the provided text.
That is a massive conceptual leap. You aren't just teaching the AI to find information anymore. You are teaching it to recognize the absence of information.
Yes.
You're teaching it to say, I don't know.
Exactly. Mathematically teaching an AI humility. It had to learn to analyze the semantic overlap between the question and the text, and if that overlap didn't cross a certain confidence threshold, it had to output a null response.
I don't...
Right. It was a monumental step forward in making these systems trustworthy for actual human use.
So that's Squad.
Yeah, but Squad isn't the only way to train them. There is also Trivia QA, which is fascinating because it was actually built by trivia enthusiasts.
Really, just trivia nerds.
Yep. And it offers high-quality supervision by providing an average of 6 independent evidence documents per question, rather than just one isolated paragraph.
Which mirrors real human research.
Yeah.
If you're listening to this and you're trying to figure out a complex trivia question, you don't just look at one web page. You open 6 tabs, you read across all of them, and you synthesize the truth.
Exactly.
It forces the AI to cross-reference, which is brilliant.
It is. Now, moving away from span extraction, another fascinating testing format is the CLOSE format. CLOZE.
Okay, the CLOSE format.
Think of it as a highly complex fill-in-the-blank test. The dataset commonly used here is the CNN Daily Mail dataset, which consists of news articles and their bullet point summaries.
Right.
But researchers do something very clever to prevent the AI from cheating on the test. They anonymize the entities.
Wait, what do you mean by cheating? How does an AI cheat on a reading test?
Well, neural networks are essentially massive statistical engines. They are absolutely brilliant at finding lazy correlations.
Okay, sure.
If a model reads a million news articles, it might notice that the words Jeremy Clarkson, producer, and Strzok appear together very frequently in the dataset.
Because it was a huge news story.
Right. So if you ask it a question about a producer getting struck, it might just spit out Jeremy Clarkson based purely on statistical co-occurrence.
Oh, I see.
It does that without actually understanding the grammar or the meaning of the specific sentence it's currently reading.
It's just playing the odds. It's not reading, it's just guessing based on its historical memory of internet drama.
Exactly. It's taking the path of least resistance.
Yeah.
So in the close format, researchers strip out the names. A sentence like, the BBC producer allegedly struck by Jeremy Clarkson will not press charges, becomes, ENT 381 producer allegedly struck by ENT 212 will not press charges.
Here's where it gets really interesting, because this is brilliant. You are turning the news into an intense game of Mad Libs.
Essentially.
By masking out Jeremy Clarkson and replacing it with a generic tag like ENT212,
Yeah.
you are forcing the AI to actually parse the linguistics of the event.
Exactly.
It can't rely on Twitter drama or statistical memory. It has to look at the verb struck and the noun charges, understand the relationship between a subject and an object in that specific sentence, and figure out what type of entity belongs in that blank.
Yes, it has to solve 2 problems simultaneously. First, semantic typing, this blank, a person, a place, or a corporation.
Right.
And second, contextual extraction. Based on the verbs and adjectives around this blank, which specific entity from the source text fits here? It forces true structural understanding of the language.
So we have span extraction, where it just highlights. We have close, where it fills in the blanks. What happens when the answer isn't a neat little quote you can highlight or a single word? What if the question requires the AI to synthesize an original thought?
Well, then you move into generative QA.
Generative QA.
Right. In this format, the AI is not just pointing at a page or filling a blank. It is generating a free text answer from scratch, token by token.
Oh, wow.
The classic example is giving the AI a summary of a movie plot, like Ghostbusters 2, and asking a complex question that requires combining details from different parts of the plot summary into a completely newly drafted sentence.
But if I'm a researcher, how do I grade that?
It's tough.
Because with the span solution, grading is binary. Did it highlight the right word? Yes or no? But with generative QA, there are 1,000 different ways to write a perfectly correct sentence.
And that is the core difficulty of generative QA right there. It is notoriously hard to evaluate automatically at scale. We have to rely on natural language generation metrics like BLEU or Rouget.
Okay, I hear those acronyms constantly in AI spaces, BLU and Rouge. Break those down for us. How do they actually measure if a generated sentence is good?
Essentially, they measure mathematical overlap. They compare the AI's generated answer against a reference answer written by a human.
Okay.
They break the sentences down into n-grams, which are just chunks of words. A unigram is 1 word, a bigram is 2 words in sequence, and so on.
Right.
If the human reference says, the ghost was captured by the team, and the AI generates, The team successfully captured the ghost. Metrics like BLEU calculate how many of the AI's engrams appear in the human's text.
But wait, I see a glaring flaw there.
What's that?
What if the AI generates a sentence that means the exact same thing but uses completely different vocabulary?
Yeah.
Like, what if it says, the Spectre was detained by the squad? To a human, that is a perfectly correct answer, but to an engram metric like BLEU, there is almost zero word overlap. Does it score a 0?
You've identified the exact limitation of these metrics. Yes, it would score very poorly. BLEU and Rouge are largely blind to synonyms and deeper semantic equivalents.
Wow. So they just fail on good writing.
Yeah, they are blunt instruments. They aren't perfect, but when you are evaluating the performance of a model across 100,000 generated answers during training, you can't pay humans to read all of them.
Right. That would take years.
Exactly. You need an automated metric, and mathematically measuring a kubigram overlap is just the standard tool we have, despite its obvious flaws.
Okay, so we understand the exams. We've got Squad, Trivia QA, Closed Generative. We know what we are testing for.
Right.
Now we really need to look at the architecture. How do these AI systems actually process millions of documents to take these tests? Because if I search for a fact, the AI has to sift through Wikipedia. Reading millions of pages in real time sounds like it would completely overwhelm the processing power of a standard computer.
Oh, it absolutely would.
Yeah.
Which is why the architecture of QA systems has evolved so dramatically.
Yeah.
But to appreciate where we are now, we have to look at the old paradigm first. We have to look at the classic QA stack.
Okay, let's walk through it. How did we do this 10 years ago?
The classic QA stack was an elaborate, highly compartmentalized, multi-stage pipeline. It was a sequence of very explicit modules.
Like an assembly line.
Exactly. First, a user's question comes in. The system immediately runs something called WH-type resolution.
WH-type resolution.
Right. It runs a syntactic parse on the question to figure out the expected answer type. If you ask, where's the Eiffel Tower? The WH resolution module tags the query with the entity type location. If you ask who built it, it tags it as person.
Okay, that makes logical sense. Step 1, figure out what category of thing I'm looking for. What's step 2?
Step 2 is document retrieval, pulling up potentially relevant web pages based on keywords. Step 3 involves filtering those documents, trying to extract sentences that match the location tag we generated back in step 1. Step 4 ranks those candidate sentences. And then step 5 outputs the top result.
I mean, that sounds incredibly logical. It sounds like a highly organized detective agency.
It does, right?
Yeah. A case comes in. The chief categorizes it as a missing person, hands it to the records department. Records pulls 50 files, hands them to an analyst. Analyst throws out 40 files, hands the remaining 10 to the lead detective. It's a solid pipeline.
It is logical in theory, but in practice, pipelines are incredibly brittle. What is the fundamental flaw of a 5-step pipeline?
Well, I'd say compounding errors. If the chief at step 1 incorrectly tags the question as looking for a company instead of a location, the entire rest of the agency is doomed. They're spending all their time looking for the wrong thing.
Exactly. In a multi-stage pipeline, errors multiply. If your WH resolution is 90% accurate, and your document retrieval is 90% accurate, and your sentence filtering is 90% accurate, by the time you reach the end of a 5-step pipeline, your overall system accuracy has plummeted to around 59%.
Oh, wow, that's terrible.
It is. Every time you hand data from one discrete module to another, you lose information, and you introduce the potential for catastrophic failure.
So if the pipeline is too brittle, what replaced it? What is the architecture today?
The field moved to a 2-stage paradigm that completely dominates state-of-the-art models today. It's called the retriever-reader architecture.
Retriever-reader. Okay, so instead of a 5-step bureaucracy, we just have 2 entities.
Yes, 2 highly specialized neural networks working in tandem.
Yep.
Stage 1 is the retriever. When your question comes in, the retriever's only job is to blast through a massive corpus, like the entirety of Wikipedia, and grab a small handful of candidate documents.
But it doesn't read them.
No, it doesn't read deeply. It doesn't try to find the final answer. It is optimized purely for speed and high recall, meaning its goal is to just make sure the document containing the answer is somewhere in the stack it grabs.
Okay, so the retriever is like a hyper-fast librarian. You yell a question and they sprint into the stacks, grab 5 books that seem highly relevant, and just slam them on the table in front of you.
That's a great analogy. And sitting at that table is stage 2, which is the reader.
Right.
The reader ignores the millions of other books in the library. It takes the specific candidate documents handed over by the retriever, and it parses them in a single, intense reading comprehension phase. It does the heavy cognitive lifting to extract the exact answer span from that localized text.
So the reader is the Genie speed reader. They don't know how to find a book in the library. But if you put 5 books in front of them, they can scan the pages, point to a single sentence, and say, here is your answer.
Exactly.
By splitting the job into 2, you avoid the computational nightmare of trying to deeply read the entire internet at once, while also avoiding the brittle compounding errors of the old pipeline.
Precisely. It is an elegant division of labor. But to truly grasp how powerful this is, we need to pop the hood on the reader.
Okay, let's do it.
We need to look at how a neural network actually reads a paragraph.
Yeah.
Because at the end of the day, a computer doesn't have eyes or a biological brain. It doesn't understand language the way we do. It literally only understands numbers.
Right. If you're listening to this, you're probably thinking, okay, I get the speed reader metaphor, but mechanically, how does a machine look at a paragraph and know which specific word is the answer? It's just code.
It relies on a concept called document attention, which is usually powered by transformer models like BERT.
BERT, yeah.
The fundamental mechanism here is mapping text into a joint latent space.
Let's slow down there. Joint latent space. We need to translate that for anyone who isn't a data scientist. What is a latent space?
Imagine a massive multidimensional map. When a model like BERT processes a word, it doesn't store it as text. It translates the meaning of that word into a mathematical coordinate on this map.
Okay.
Words that share semantic meaning are plotted close together. Dog and puppy are near each other. Dog and carburetor are very far apart.
Okay, so it's mapping meaning into physical space. It's a universe of concepts.
Yes. Now, the key word is joint. A joint latent space means the model takes the user's question and the paragraph provided by the retriever, and it encodes them both onto this exact same map simultaneously.
At the same time?
Yes. It is mathematically measuring the gravitational pull, the semantic overlap between the concepts in the question and the concepts in the various sentences of the paragraph.
So it's looking for where the question and the paragraph intersect in this universe of meaning. But how does it actually feed the text into BERT? Does it just dump the whole Wikipedia page into the algorithm at once?
No. Transformer models like BERT have strict token limits, and they expect highly structured formatting. You build a specific sequence.
How does that look?
First, you insert a special token called the CLS token, which stands for classification. This acts as a flag telling the model, pay attention, we are about to start a sequence task.
Okay, CLS.
Following the CLS token, you feed it segment A, which is the exact text of the user's question. Then you insert a SEP token, which is a separator to clearly define a boundary. Finally, you feed it segment B, which is the paragraph of text.
So it's CLS token, question, separator, paragraph. It's like setting up an algebraic equation for the AI.
It is. And once BERT processes that sequence, using its attention mechanisms to weigh the importance of every word against every other word in both the question and the paragraph, it outputs something beautifully simple.
That's that.
It just outputs probabilities for 2 coordinates. The most likely starting word of the answer and the most likely ending word of the answer.
It literally just gives you the index coordinates of the highlight.
Exactly. But here is the massive real-world engineering hurdle. To train that BERT reader to know what a good highlight looks like, you need datasets like SQuAD, where a human has explicitly paired a question with a specific paragraph.
Right, the gold standard data.
Right. But what if you don't have that? What if your training data is just millions of trivia flashcards?
Oh, I see the problem. If I have a digital flashcard that says Q, who directed Jurassic Park, A. Steven Spielberg, I have the absolute truth. But I don't have the paragraph of context.
Exactly.
I don't have the Wikipedia page to teach the AI how to find that truth in the wild. I just have the final answer.
Right. And paying human annotators to go through 10 million trivia flashcards, search Wikipedia for every single one, and manually highlight the exact paragraph where the answer lives is financially impossible.
It would cost tens of millions of dollars.
Absolutely. So researchers had to invent a workaround, which is called distant supervision.
Distant supervision. How do you supervise an AI from a distance?
You automate the creation of the training data. You take the question from your trivia flashcard, who directed Jurassic Park, and you use a basic search engine to pull up a bunch of Wikipedia paragraphs.
Okay.
You don't know for sure if these paragraphs are perfect examples, but you run a simple script. If the retrieved paragraph contains the exact string of text Steven Spielberg, you make an assumption.
A leap of faith.
Yeah. You assume this paragraph contains the contextual answer to the question. You pair them up, and you feed it to the model as a positive training example.
You're basically taking a calculated bet. You're saying, look, I know the answer is Spielberg. I did a search for Jurassic Park. This paragraph mentions both Jurassic Park and Steven Spielberg. I'm going to bet 99% that the sentence structure connecting those two things is the correct context. So I'll use it to train the AI's reading comprehension.
Exactly. Now, does it introduce statistical noise?
Ah.
Yes. Occasionally, the paragraph might mention both entities, but in a totally unrelated context.
Like they're both mentioned in a list of 90s pop culture icons or something.
Exactly. But at scale, when you are processing millions of examples, the signal overpowers the noise. We call this a silver data set.
Silver.
Yeah, it lacks the perfect handcrafted purity of a gold standard human data set like Squad, but it is silver. It is
Yeah.
highly valuable, and more importantly, it is virtually free to generate at massive scale.
Gold data is perfect, but expensive. Silver data is slightly noisy, but infinite. I love that. And infinite data is what allows researchers to build robust frameworks. Which leads us to a specific architecture highlighted in the notes called Bertzarini.
Yes. Bertzarini is a prime example of putting this entire retriever-reader concept into a working system. It integrates a traditional open-source search engine index called Answerini with a modern BERT reader.
How does the handoff work in Bertzarini between the retriever and the reader?
The first stage, the retriever, uses a classic bag-of-words search algorithm called BM25 to grab segments of text from Wikipedia. And it can grab them at different granularities, like whole articles, specific paragraphs, or just individual sentences.
Okay.
It passes a stack of these segments directly to the BERT reader.
Okay, stop there. Because if the retriever hands the BERT reader 5 different paragraphs from 5 different Wikipedia articles, how does BERT decide which one has the best answer?
That's the trick.
Because if you give a human student 5 paragraphs and say, find the answer, they might find a decent, poorly phrased answer in paragraph A, but a perfect, clear answer in paragraph B. How does the AI mathematically compare them?
That is the crucial engineering challenge. And to understand how Bertzarini solves it, you have to understand how standard BERT grades its own answers.
Okay, how does it?
In a standard BERT model, the final mathematical layer is called a softmax layer.
Softmax, what does that do?
Well, without getting bogged down in the complex calculus, a softmax layer forces the model to pick a winner within a closed system. It takes the probabilities of all the possible answer spans within a single paragraph, and it mathematically squashes them so they add up to exactly 100%.
Okay, so softmax is essentially grading on a curve. No matter how bad the students are, someone has to get an A. The probabilities have to equal 100.
That is a perfect analogy. If you give standard BERT a paragraph that contains the perfect answer, the best span might get a 90% probability score, and the other random spans share the remaining 10%.
Makes sense.
But if you give standard BERT a paragraph that doesn't actually contain the answer at all, the softmax layer still forces a curve. It will pick the least bad string of words in that useless paragraph and give it a high artificial score, maybe 85%. Because the math demands that all probabilities in that paragraph sum to 100%.
Oh, wow. I see the catastrophic flaw here. If the retriever hands BERT paragraph A, which is complete garbage, and paragraph B, which has the perfect answer, BERT processes them separately.
Yes.
Paragraph A's softmax curve might spit out an 85% confidence score for a terrible answer. Paragraph B's softmax curve might spit out a 90% confidence score for the perfect answer.
Exactly. And while 90 is higher than 85, you can't actually trust that comparison because they were graded on entirely different curves. Paragraph A's 85% is a lie. It's the valedictorian of a terrible school.
Right.
You cannot compare the scores across different segments. So what is the elegant fix implemented in Bertzarini?
Do they just remove the curve?
Precisely. To allow aggregation and true comparison of results across all those different segments, they simply remove the final softmax layer over the different answer spans.
So removing the softmax layer fixes our grading curve problem. You get raw, unnormalized mathematical scores for every span across every paragraph. You can line up the raw score from paragraph A against the raw score from paragraph B, and the best absolute answer wins, regardless of which book the librarian handed you.
It is brilliantly simple.
Hmm.
But, even with perfect global grading, if the retriever fed the reader garbage paragraphs in the first place, we still fail. The reader can only extract from what it is given.
Right. Garbage in, garbage out.
Exactly. How do we make sure the retriever isn't just handing us junk? How do we tune this engine for maximum performance?
We need to train the system to handle noise.
Exactly. And one of the most effective techniques discussed is multi-passage training.
Multi-passage.
Historically, models were trained by looking at one passage at a time. But researchers realized that if you want the model to succeed in the real world, you have to train it on multiple passages simultaneously. And critically, you must include non-answer paragraphs, what we call negative examples, in that training batch.
Wait, if you were trying to teach an AI what an answer looks like, why would you deliberately confuse it by feeding it paragraphs that don't have the answer?
Because the real internet is mostly made of paragraphs that don't have your answer.
Oh, that's true.
If you only train an AI on paragraphs that contain gold, it becomes overly eager. It expects to find gold in every pile of dirt it looks at. By feeding it multiple passages at once during training, say one paragraph that contains the answer and 3 paragraphs that are completely irrelevant, you teach the model restraint.
You're calibrating its radar. You're teaching it what the absence of an answer looks like so it doesn't try to force a puzzle piece into the wrong spot.
Precisely. It makes the model's ability to pinpoint answers much more stable. But even with that robust training, the initial retrieval step and, the librarian grabbing the books is inherently noisy.
Always.
If you search a massive database for a keyword, you are going to pull up irrelevant documents. This introduces the absolute necessity of a component called a re-ranker.
A re-ranker. Where does that fit into the retriever-reader superhero duo? Is it like a sidekick?
It's more like a quality control editor. It's a second-stage binary classifier that sits directly between the two.
Okay.
After the hyperfast retriever pulls, say, 100 candidate passages, the re-ranker steps in. It explicitly looks at the user's question, looks at each retrieved passage, and gives it a binary score. Is this passage actually relevant to this question, yes or no?
So the workflow is, retriever grabs the 100 documents, re-ranker looks at them, throws out 90 of them as garbage, and says, actually only these 10 are worth our time. Then the reader looks at those 10 and extracts the final answer.
It's the filter.
Yes. It filters the noise so the cognitively expensive reader only expends compute power on high-quality text. But to really understand the frontier of this technology, we have to talk about the retriever itself.
Okay.
We have to talk about the leap from sparse retrieval to dense retrieval, because earlier we mentioned that the retriever uses something called BM25.
Right, BM25, which you said is a bag of word search. That's just the classic keyword search we've all been using for 20 years, right?
Yes. In the industry, we call it sparse retrieval. It is based entirely on term frequency and document frequency. It creates a massive mathematical vector representing every word in the vocabulary, which is mostly empty zeros, hence sparse, and it just counts exact word overlaps.
Let's spend a minute on this because understanding the pain of BM25 is really the only way to understand why modern AI is so revolutionary.
Absolutely.
Because BM25 is literal. If I ask a sparse search engine, how tall is the Eiffel Tower? It doesn't know what an Eiffel Tower is, doesn't know what height is. It just knows that the letters TALL form a string, and it scans millions of documents looking for that exact string of letters.
And that introduces the most persistent headache in information retrieval, the vocabulary mismatch problem.
Vocabulary mismatch.
Natural human language is incredibly rich. We use synonyms, analogies, and varied sentence structures constantly. If a Wikipedia document says the Parisian iron structure reaches a maximum elevation of 300 meters, BM25 will likely rank that document very low or miss it entirely.
Because the document doesn't use the word tall and it doesn't use the word Eiffel.
Exactly.
The answer is staring the machine right in the face, but because the author used the word elevation instead of tall, the keyword search is completely blind to it.
Exactly. Sparse retrieval has no concept of semantics. It only has string matching. This fundamental flaw is what drove the paradigm shift to dense representations.
Dense vectors. This is where the magic happens. How does a dense vector solve the vocabulary mismatch problem?
Instead of a massive, mostly empty vector that just tallies exact words, we use a neural network to compress the entire semantic meaning of a passage into a short, dense array of numbers. A dense vector captures the context, the concepts, and the relationship between the words. It encodes the idea of the text. The notes highlight 3 major architectural breakthroughs that leverage this: ORQA, RAG, and DPR.
Okay, let's unpack those. What did ORQA do?
ORQA stands for Open Retrieval Question Answering. Its big breakthrough was introducing an inverse closed task objective during the pre-training of the retriever.
Like the Mad Libs thing.
Yes. It taught the retriever to understand context by masking out sentences and forcing the model to predict the surrounding text. It was one of the first dense models to demonstrably mathematically outperform BM25 sparse retrieval. It proved the concept worked.
And RAG. I feel like RGRAE is the most hyped acronym in tech right now. Retrieval Augmented Generation.
Oh, it is?
If I'm following our logic so far. We have the retriever grabbing documents, and usually the reader just highlights a span of text, but the generation part of RAG makes me think we were swapping out the reader. Are we hooking the retriever up to a text generator instead?
That is exactly the leap. RA takes the dense retriever and a generative model and trains them end to end.
Wow.
Instead of just highlighting a pre-existing sentence, RA treats the retrieved documents as latent variables, basically as a customized memory bank. It feeds those retrieved documents into a generator, and the generator synthesizes a completely new, fluent, custom essay summarizing the answer.
It's like having the librarian hand the speed reader a stack of books, but instead of the speed reader just pointing to a paragraph, the speed reader absorbs the facts and writes you a personalized report.
Yes.
That is incredibly powerful. And what about the third one, DPR?
DPR stands for Dense Passage Retrieval. While RAG focused on the generation end, DPR is purely focused on revolutionizing the retrieval step itself.
Okay.
DPR uses two separate BERT networks. One encodes all the millions of passages of Wikipedia into dense vectors and indexes them offline. The other encodes the user's question into a dense vector in real time.
So we have millions of document vectors floating in our joint latent space, and we introduce the question vector. How does the computer actually match them up?
It uses something called MIPS, which is Maximum Inner Product Search.
Okay, you're going to have to explain my PS. How does a computer find the nearest neighbor in a mathematical space containing tens of millions of documents without taking 5 hours to calculate the distance to every single one?
Think of it visually. Imagine a massive 3D room.
Okay, a 3D room.
Every document in Wikipedia is a tennis ball suspended somewhere in this room. Documents about biology are clustered in one corner. Documents about French history are clustered in another. Now, your question enters the room as a red golf ball. MIPS is the mathematical algorithm that efficiently draws a line from your red golf ball to the closest tennis balls.
But how does it do it efficiently? Doesn't it have to measure the distance to every single tennis ball?
No, and that's the brilliance of it. It uses indexing structures that divide the room into zones. If the red golf ball appears in the French history corner, the algorithm instantly ignores the biology corner entirely. It only calculates the exact geometry for the local neighborhood of vectors.
That makes sense.
MIPS allows DPR to find the closest semantic matches in milliseconds, proving that dense retrieval isn't just a neat academic trick. It is fundamentally faster and better than sparse keyword methods.
I want to make sure you, listening right now, really internalize this shift, because this is the core of the AI revolution.
Yeah, it really is.
We were comparing sparse retrieval, like BM25, to looking up a book purely by counting how many times a string of letters appears. It is rigid. If you search for funny dog, it will only find pages with those exact words.
Right.
But dense retrieval, like DPR, is finding a book based on its conceptual vibe. It plots the ideas in that 3D room. So if you search funny dog, the dense vector algorithm realizes that the phrases hilarious puppy or comical canine live in the exact same physical coordinates in that universe of ideas, and it retrieves them even if the exact keywords are completely missing.
That is a brilliant summary. Dense vectors bridge the vocabulary gap. They understand that different words can mean the same thing.
It feels like once you crack that, once you have dense vectors and MIPS and a BERT reader, you've basically solved information retrieval. You encode the query, find the closest document in the 3D room, extract the span, and you're done.
You would think so.
But no.
No, finding an answer in a single document is an incredible engineering feat. But human knowledge rarely lives neatly packaged in a single sentence on a single Wikipedia page.
True.
The world is complex. And that brings us to the final and, frankly, most computationally daunting topic of this deep dive: multi-hop reasoning.
Multi-hop, meaning the answer isn't in one place. We have to jump from document A to document B.
Exactly. The AI has to hop across multiple completely independent documents to piece together a logical chain. Let's use a very simple example to illustrate the multi-hop problem.
Let's hear it.
Imagine two separate sentences. Sentence 1, Jack went up the hill. Sentence 2, Jack put down the pail. The question is, where did he put the pail?
Well, the answer is the hill. But if I think about how my brain just did that, it's actually a multi-step process.
It is. Think about the logic required for an AI to solve that. First, the AI must resolve the pronoun. It has to know that the word he in the question refers to the specific entity, Jack, in the second sentence.
Right.
Then it has to realize that the second sentence, Jack put down the pail, does not actually contain a location. the answer isn't there.
Right. So to find the location, it has to hold on to the action, put down the pail, hop backward to the first sentence, Jack went up the hill, and conceptually connect the location of the first sentence to the action of the second sentence.
For a human, that takes zero effort. We synthesize context subconsciously. But for an AI, that requires mathematically chaining logic across separate pieces of information. And why is this so hard on a macro scale? Because the internet doesn't perfectly hyperlink all related concepts together.
Let's apply this to the real world. Give me a real multi-hop search scenario.
Okay. Imagine asking an AI, where was the wife of the author of The Great Gatsby born?
Oh, wow. Okay, so I can't just search that exact string. I have to find out who wrote the book, F. Scott Fitzgerald.
Yes.
Then I have to pivot, take his name, and find out who his wife was, Zelda Sayre. Then I have to pivot again, take her name, and find her birthplace, Montgomery, Alabama. That is 3 distinct hops across 3 entirely different Wikipedia pages.
Exactly. An AI system must chain this logic across isolated documents. It has to become an active investigator.
Okay, so how do we engineer a system to do that? You can't just use standard dense passage retrieval for that because standard DPR only encodes the original question once, right?
Right. If standard DPR encodes, where was the wife of the author of Gatsby born? It will find the Gatsby page, see that the birthplace isn't there, just fail. It doesn't know how to keep searching.
Precisely. So researchers developed an elegant mathematical loop called multi-hop dense retrieval.
How does the loop work?
It essentially runs the retrieval process iteratively. First, it uses a model like RoBERTa, which is essentially a more heavily optimized, robustly trained evolution of BERT, to encode the initial query. It searches the index and returns document 1, which is the Wikipedia page for The Great Gatsby. Okay, hop 1 is complete. We have the book page. We know the author is F. Scott Fitzgerald. But the final answer isn't there. What is the mechanism that allows it to keep going?
The system runs a second round of encoding. It takes the dense vector of the original query, and it mathematically combines it with the dense vector of document 1.
Oh, it merges them.
It merges them. Then it uses this new combined vector to search the index again.
That is wild. It's literally updating its search query on the fly based on what it just read. It's mathematically asking the index. Given the original question and the fact that I now possess the context of the Gatsby page, what is the next most relevant document?
Exactly. It's learning as it reads. That second search pulls document 2, the page for Zelda Fitzgerald. It combines that context, searches again, and pulls document 3, Montgomery, Alabama, where the reader finally extracts the answer.
Unbelievable.
And to push the boundaries of this technology, researchers have created incredibly difficult data sets designed specifically to break these models. The 2 prominent ones are HotPotQA and Fever.
Let's talk about HotPotQA first. What makes it tougher than standard QA?
HotPotQA is a crowdsourced dataset of questions that explicitly require finding and reasoning over multiple supporting documents across Wikipedia hyperlink graphs. But here's the kicker, the thing that makes it so difficult. It requires sentence-level supporting facts.
What does that mean practically?
It means the AI cannot just spit out the final answer. It has to explicitly point to the specific sentences in multiple different documents that prove its logic path.
Oh, what?
If it says Montgomery, Alabama, it has to output the sentence from document A, proving Gatsby's author, the sentence from document B, proving the wife, and the sentence from document C, proving the birthplace. It forces the AI into what we call explainable QA.
Show your work.
Exactly.
It's the math teacher approach. I don't just want the answer. I want to see the exact formula of how you got there, which honestly is so important for trust. If an AI gives me a wild answer about a medical symptom, I don't just want the diagnosis. I want to see the 3 medical journals it hopped across to reach that conclusion.
Explainability is the foundation of trust in AI. And trust is the central theme of the other major dataset, FEVER, which stands for Fact Extraction and Verification. FEVER is essentially an automated fact-checking dataset.
Oh, this is incredibly relevant right now. An AI that fact-checks the internet, how do you even build a data set for that?
The creators took thousands of factual Wikipedia paragraphs, and they paid human annotators to deliberately alter the keywords to create false claims. So they generated a massive database of claims, some demonstrably true, some subtly false. The AI's job is not to answer a question, but to read a claim, retrieve multiple evidence documents from a clean corpus, chain the logic together, and then classify the claim into one of 3 distinct categories.
Which are?
Supported, meaning the evidence proves it's true; refuted, the evidence proves it's false; or not enough info, meaning the evidence is ambiguous or incomplete.
That is fascinating. It's elevating the AI from a search engine to a judge. It's judging the validity of a statement based on evidence it has to hunt down itself.
Yes.
But wait, if multi-hop requires gathering all these different pieces of evidence from different documents, doesn't that make the re-ranker component we talked about earlier absolutely critical?
How so?
Well, think about the compounding error problem again. If the retriever pulls a bad document on hop 1 and feeds that garbage context into the query for hop 2, the whole logic chain is poisoned.
Yes, entirely.
Without a strict re-ranker aggressively filtering out the noise at every single hop, the AI is just staring at a chaotic conspiracy board, right? Connecting completely unrelated thumbtacks with red string because it got confused on step 1.
That is an incredibly astute observation.
Yeah.
You have pinpointed the exact vulnerability of multi-hop systems. If you look at the benchmark results for datasets like HotBotQA and Fever, simple single-shot retrieval without re-ranking performs abysmally.
I bet.
The noise overwhelms the signal. When you are gathering multiple documents iteratively, you exponentially increase the chance of pulling in irrelevant data that derails the latent vector. Therefore, rigorous aggressive re-ranking at each hop is essential to keep the logic chain sound. The AI must constantly evaluate, does this specific document actually support my current chain of thought, or is it a distraction?
It's so incredibly complex. We've gone from just counting how many times the word tall appears on a page to engineering an AI that literally acts as a research assistant, reading multiple books, dynamically updating its search based on what it learns, verifying facts, and showing its work.
It is a massive evolution.
Yeah.
If we step back and look at the trajectory we've covered, a few core principles of modern NLP become clear.
Let's summarize them.
First, the two-stage reader-retriever framework has entirely superseded the old pipelines and is the undisputed standard for open domain QA. Second, dense retrieval, using semantic vectors in a latent space rather than sparse keyword counting, is vastly superior because it understands meaning.
Right.
And third, interestingly, simple, efficient pipelining, like doing retrieval, then a strict re-ranking pass, then reading in distinct, highly optimized steps, is currently outperforming some of the overly complicated end-to-end black box models. Sometimes breaking a complex cognitive task down into specialized, highly tuned components is still the best engineering approach we have.
Wow. We have covered a massive amount of ground today. For you listening, we've taken a journey from understanding the foundational flavors of factoid and opinion QA right through the intense testing mechanics of Squad's unanswerable questions and the closed format's Mad Libs.
It's been a lot.
It has. We've unpacked the brittle failure of classic pipelines and celebrated the retriever-reader dynamic duo. We looked under the hood at BERT, joint latent spaces, and the mathematical beauty of dropping the softmax layer to compare answers globally.
Yep.
We explored how dense vectors plot the conceptual vibe of information to solve the vocabulary mismatch problem. And finally, we tackled the absolute frontier of multi-hop reasoning and automated fact-checking with Fever. It is a masterclass in how machines are learning to truly comprehend human knowledge.
It is a rapidly accelerating field.
Yeah.
The transition from keyword search to deep semantic reading comprehension is fundamentally changing the fabric of how we interact with information on a daily basis.
And that leads me to a final thought I want to leave you with, directly building on this idea of Fever and multi-hop reasoning. We just spent an hour talking about how AI is mastering the ability to hop across completely unconnected documents to verify existing facts.
Right.
But what happens when we unleash this capability, not just to verify old facts, but to discover new ones?
Oh, wow.
Think about it. If an AI can read an obscure biology paper published in 1998, extract the dense meaning into a latent space, and then multi-hop its way to a chemistry paper published in 2024, making a synthetic, logical connection between two disparate pieces of data that no human researcher has ever put together in the same room, does the AI transition from just answering questions to actually generating net new human knowledge?
That is a profound question. We are moving from the era of retrieval to the era of discovery.
It's no longer just a hyper-fast librarian grabbing books. The librarian is reading the books, connecting the dots across decades of research, and writing a new chapter of science while we sleep. It's absolute magic.
It really is.
Thank you so much for joining us on this deep dive into open domain question answering. Keep questioning the information around you, keep exploring those latent spaces of meaning, and we will see you on the next one.